Hello, this is Tarun from Science Department, VIT Chennai, and this video it's an attempt to illustrate few concepts on AC circuit analysis. We'll be concentrating on LCS circuits and power analysis. This video it's also my part of my digital assignment 3 assigned to me by my respectful EC faculty Dr. Jagannath M, and I heartfully thank him for giving me such an opportunity. So let's start by having a look at the first question. It's from Alexander book, Circuit Theorems. First question says, a choke coil is connected across a 250 volt 50 Hz supply. If the input current be 10 ampere and power loss in the coil be 1 kilowatt, find the impedance, resistance and inductance of the choke. What is the power factor of the circuit? What would be the value of the input current if a capacitor of C farad is connected in series with the coil such that the power factor becomes unity? So let's see the solution. The solution says, according to the question given, is supply voltage is 250 volts, angular frequency is 50 hertz, current is equal to 10 ampere, power loss is 1000 watts. Impedance is equal to Vs by I. As we usually know, V is equal to I into impedance. So 250 by 10 is 25 ohms, and the power loss is I square R, which is 10 square R is given 1000, so R is equal to 10. And we also need the inductive reactance, which is impedance square minus resistance square the whole root, which we get out to be 23 ohms. And the power factor is resistance upon impedance, which is 10 upon 25 is 0.4. And also assuming capacitor C is connected in series with the coil such that the power factor becomes unity, therefore capacitive reactance equal to inductive reactance. So 1 upon 2 frequency into C into pi should be equal to 23, which is the power factor. So C is equal to 1 upon 2 pi 50 23, which we are converting frequency into angular frequency, which comes out to be 138.5 microfarad. Current also I is equal to V voltage by impedance, which is also equal to V by R. Since the capacitive reactance and inductive reactance are same, they cancel out. So the answer comes out to be 250 by 10, which is equal to 25 ohms. Now let's see the next question. The next question says, in a RL series circuit, inductance is variable. If an AC voltage of V volts is applied to 50 Hz, find the maximum transfer from source to the load. So this is the circuit, this is the inductor, this is the resistor, and this is supply. As it says, current is equal to voltage by inductance, which is V by impedance. I is equal to V by impedance, so is equal to V by the whole root of R square plus inductive reactance square. At it has only the inductor and it doesn't have a capacitor. So it turns out to be, we add an R, multiply an R and divide it by an R, so we get the constant which is VR, and we'll take it as to be K. R by Z is PF, which is constant, also cos phi. Let's take I is equal to cos phi, represents a circle of I in a polar form, as we already know. X is I cos theta, its real component, and Y is equal to I sin theta. You notice a minus sign here, negative sign. This is because as the current lags behind in the inductive circuit. I repeat, Y is negative as current lags behind in the inductive circuit. So the real part X is equal to V by the impedance into cos phi, which is V by Z into R by Z, which is VR upon Z square. We can also write this as V upon the whole root of R square plus inductive reactance the whole square into R upon the same, which is VR upon R square plus inductive reactance the whole square. So it comes out to be Y is equal to minus voltage upon impedance sin phi, which continues, we calculate, turns out to be x square plus y square is equal to v square r square by r square plus x square l square plus v square xl square upon r square plus xl square the whole square. When you calculate, it comes out to be somewhat like this, which is v by r into v upon r square by x l square, which is nothing but v by r k into v by r square, the whole square of reactance plus the whole square of inductive reactance, resistance actually r. So we get the equation of the circle, the polar form, x square plus y square is equal to v by r into x or the equation as is written here, x minus v by 2r the whole square plus y minus 0 the whole square is equal to v by 2r the whole square. Our equation, it represents a circle of radius v by 2r and center v by 2r comma 0. Therefore the x component is v by 2r and the y component is 0. Let's examine these two conditions. For inductive reactance B0, I is equal to V upon R, therefore current is maximum. For PF is equal to unity, since Z is equal to R. If XL is equal to infinity or very large, current is 0, as we can see. When XL is very large, I is equal to V by Z, which is equal to V by XL. Therefore I lags by 90 degree. PF is lagging. Therefore, PF is lagging. Real power is equal to VI cos theta. If V is constant power, then it will be maximum when I cos theta is equal to maximum. Therefore, power factor must be maximum then when it is 1. Therefore, power max is equal to VI is equal to V into V by R is equal to V square by R. This is a polar representation of the circle we just saw above with its center at V by 2R, 0 and has a radius of V by 2R. Now let's see the next question. It's in the see. It realizes the above question. It says in the above question, instead of varying the inductive reactance from 0 to infinity, if R is varied keeping inductive reactance constant, what would be the maximum power? I repeat, he's asking what's the maximum power. So this is the figure from the last thing as we already made. So x is equal to VR upon r square plus x square, y is equal to minus vxl upon r square plus x square. As you saw, the equation comes out to be x square plus y square is equal to v square upon r square plus xl square. Therefore, minus v upon xl into vxl upon r square plus xl square turns out to be minus vy upon xl. So the equation comes out to be x minus 0 the whole square plus y plus v upon 2xl the whole square is equal to v by 2xl the whole square. The equation just derived shows equation of a circle whose radius is v by 2xl as its center is at 0, minus v upon 2xl. Let's also see the two extreme conditions of current. When R is equal to 0, I is equal to V by Z, which is also equal to V by XL. Therefore, power factor becomes 0. It's a purely inductive circuit. When R is equal to infinity, I is equal to V upon infinity is obviously 0. And also the third case, R is V very large but not infinity. In that case, I is equal to V upon R, and at a very low magnitude when R is V, very high, current value is lower but power factor is unity. So power is V I cos theta. Since V is constant power, it will be maximum when I cos theta is max. Maximum value of I cos phi is equal to V by 2xl. Therefore, the amount of maximum power given by is power max is equal to Vi cos phi is equal to V square by 2xl. See, there is the power max factor is max when it's 1. It is Vi cos theta is equal to V square 2xl. Now we see the next question. This question says to find the two impedances Z1, Z2 are in parallel across 25 Hz, 100 volts. If Z1 is given and Z2 is given, it's asking us to find currents through Z1 and Z2. Also find total current PF of each branch and the entire circuit. So let's take acceptance 1 is equal to 1 upon impedance is equal to 1 upon the given equation, and this is the second equation, which is also, if we convert we can write in a form of susceptance and conductance. Susceptance is the real part of the equation, real part of the equation, and sorry, conductance is the real part of the equation and susceptance is the imaginary part of the equation. Let's see. Real part is equal to R1 upon R1 square plus XC1 square. V1, which is acceptance, is equal to XC1 and R1 square plus XC1. Similarly, we do this for the second question. And then it turns out to be R1 is equal to 9 ohm, XC1 is equal to 15 ohm, XC2 is equal to 10 ohm. Therefore, G1 turns out to be, by calculating, we get 0.029 more, which is okay, and G2 will get 0.424292 more. B1 is equal to 0.051 more. B2 is equal to 0.05141 more. Equivalent conductance is equal to G1 plus G2, which is given, and equivalent subscriptance Bu is equal to V1 plus B2. I1 is equal to V naught into Y1, which is also equal to V naught into G1 plus JB1, as it's the whole acceptance part. As we see the calculations, you can see, and it turns out to be 2.94 plus J 4.94 volts. I2 is V naught G2 plus JB2. Similarly, we get the current after calculation to be 7.86 plus J9 9JA. Phi 1 is tan inverse of B1 by G1. That's actually Y by X susceptance upon conductance part. It turns out to be 59 degree. In the similar way, the Phi 2 is turns out to be 39.8 degrees. Phi naught is equal to B naught upon G naught, which is 48.8 degrees, and this is the polar structure. You can see it's very nicely depicted in here. So let's go to the next question. The next question given is Z1 and Z2 are given. F is equal to 50 CPS. We need to find the net admittance power factor of the circuit, and branch currents of total currents, and also power factor of the circuit. This is a given circuit diagram. So let's see the solution. Equivalent admittance of given parallel circuit is Y. Y is equal to Y1 plus Y2, which is nothing but acceptance 1 plus acceptance 2. Y1 is equal to 1 upon Z1, as we already seen. Y2 is also the same. Here R1 is equal to the given values, R2, all the given values we find out using this equation, which is G1 is equal to R1 by R1 square plus XC1 square is equal to, comes out to be 0.062 more, and G2 comes out to be 0.096 more. The net conductance G0 is equal to G1 plus G2 is equal to 0.158 more. In similar way, we'll calculate B1 and B2, which is XC1. For B1 it's XC1 upon R1 square plus XC1 square. B1 turns out to be 0.12 more, and B2 turns out to be 0.45 more. The equivalent susceptance B0 is equal to B1 minus B2, as it lags, which is 0.12 minus 0.045, turns out to be 0.075 more. Equivalent admittance is Y is equal to Y1 plus Y2, which is equal to G1 plus G2 plus J B1 minus B2 is equal to 0.158 plus J 0.075 more. Branch currents I1 is equal to G1 plus JB1 into V0, which is equal to this 0.62 plus 1.2 J ampere. I2 turns out to be I2 turns out to be 1.58 plus 0.75 J amp. And the cos component cos phi naught is equal to cos of tan inverse B1 minus B2 upon G1 plus G2. Cos, it comes out to be cos 25.39 degree, which is equal to 0.9. Let's go to the next question. The next question he asks, what would be the value of C such that the input power factor is unity for any frequency of the source. So this is the given circuit diagram. Let's see the solution. See, the impedance is equal to J4 plus 4 into J4 upon 4 plus J4 minus into minus J upon omega C. We get after solving this, we'll get to know that it's minus J upon omega C plus J4 plus J 16J into 4 minus 4J upon 32. If we solve this, the equation turns out to be minus J upon omega C plus J 6J plus 2. So for the power factor to be unity, it will be only reactive part of impedance Z. If it will be only unity if it's the reactive part of impedance is equal to 0. Therefore, if omega C is 6, we gotta cancel out the J component. Therefore, C is equal to 1 upon 6 omega is equal to 1 upon 6 into 314 is equal to 796 microfarads. This is how you solve a question for power loss. Power factor, which should be 1. In that case, the part of impedance, the reactive part of impedance, should be 0. So by that, now we'll see the next question. Next question, there's an AC bridge shown obtain the condition for the bridge balance. It's same as depicted in a DC case, so we have to balance this. In such a case, condition of a bridge should give no current through detector D. This detector D shouldn't detect any current. Therefore, the drop across AB and it should be equal to drop across AD, and drop across BC should be equal to the drop across CD arm. Therefore, by giving, let's see, I1 into impedance 1 should be equal to I2 into impedance 2. Therefore, and also I1 into impedance 3 is equal to I2 into impedance 4. Combining these equations, we get to see that impedance 1 into impedance 4 is equal to impedance 3 into impedance 2. So by putting it in a polar form, we get that is impedance 1 into impedance 4 is equal to impedance 3 into impedance 2 with those angles particular. For this we get phi 1 plus phi 4, and here we get phi 3, phi 2 plus phi 3, as whenever we multiply two impedance any complex values, the theta gets added up. So now let's go to the next question. In this question we need to find the current locus of a circuit, series RC circuit, and find the maximum power. So let's see the solution. This is the circuit diagram. So we'll find the drop across resistor and capacitor, and given as VR is equal to IR and VC is equal to I into capacitive reactance. And the supply voltage be V. So V square is equal to VR square plus VC square. V is equal to I, the whole root of R square plus XC square. I comes out to be V upon the whole root of RC square plus XC square. V upon XC into xc upon the whole root of rc square plus xc square. So it turns out to be v upon xc sine theta, where sine theta is equal to xc upon z in series RC circuit. So I is equal to k sine theta, v upon kc, it's taken to be a constant k, as it's a constant, it's not a variable property. And also above equation represents a circle in polar coordinates. To represent the circle in rectangular coordinates, let's say I cos phi is equal to x and I sin phi is equal to y. Therefore x is equal to v upon r square plus xc square into r upon r square plus xc square, which turns out to be vr upon r square plus xc square. And also let's note that in an RL series circuit, I is equal to v upon impedance, which is equal to v upon the r square plus xc square, and also where cos component cos phi is equal to r upon z. Y is equal to I sin phi is equal to v upon r square plus xc square into xc upon rc square plus r square. Vxc into r upon r square plus xc square. Let's square these both equations, add them together. We get x square plus y square is equal to v square x square upon r square plus x square plus v square r square upon r square plus xc square the whole square. This turns out to be v square plus upon rc square plus xc square. So we get an equation saying v upon xc into y, or x square plus y square is equal to v upon xc into y. Forming an equation of a circle, we get to see that x minus not 0 the whole square plus y minus v upon 2xc the whole square turns out to be v upon 2xc the whole square, which is the radius. The above equation represents a circle whose radius is v upon 2xc and center is at 0, comma v upon 2xc. Current locus diagram is shown. Let's see this diagram. This diagram is the locus of the current. When R is equal to 0, current I is equal to V upon Xc and leads voltage by 90. OM is equal to I cos phi. ON is equal to I sin phi. Maximum power will flow when OM is maximum. Therefore, when the value of OM is V upon 2Xc, PF, the power factor becomes cos 45 degree, which is 0.707. Therefore, max power becomes VI max is equal to V into V upon 2Xc into V square by 2Xc volts. Now let's see in the next question. In the next question, there is a voltage. It's given a voltage of 200 volts, 50 hertz is applied to an RLC series circuit where VR is equal to 170 volts, VL is equal to 150 volts, and VC is equal to 100 volts. The circulating current being 4 ampere. Find power factor of circuit and power loss provided inductance has a inherent resistance a part in it. So this is the voltage drop across the resistor, across the inductor, and across the capacitor. Let's take the current to be flowing in this direction. We have given the values, and this is the circuit diagram of the series LCR circuit. Let's see the solution. So VR is equal to, as given, these are the values that are given, and let's see. So as we can solve it, R is equal to 170 upon 4 as V is equal to IR, which comes out to be 4 to 2.5 ohms, and also VL is equal to 150 volts. The impedance turns out to be 150 upon 4, which is the impedance 1, which is of the inductor, turns out to be 37.5 ohms. And the VC is equal to 100 volts, so inductance of the capacitor turns out to be 100 by 4, which is 25 ohms. Z is the total impedance of the circuit. Z is equal to V upon I is equal to 200 by 4 is equal to 50 ohms. And also R plus RL plus JXL is equal minus J upon omega C is equal to Z. So solving these equations and substituting values, we get out to be 42.5 plus RL the whole square plus XL minus 25 the whole square is equal to 50 the whole square. So we get these two equations, which is ZL is equal to RL plus JXL is equal to 37.5, and also RL square plus XL square is equal to 37.5 square. We can, by solving this, we get out RL is equal to 0.52x6 XL minus 14.08. This is the equation we get. XL is equal, and by solving this, we can get XL is equal to 37.25 ohm and RL is equal to 5.5 ohm. The power factor of the circuit is equal to RL plus R upon Z, which is equal to 42.5 plus 5.5 and 50, which is equal to 0.96. Power loss is equal to I square RL plus R, which is equal to 5.5 plus 42.5 into 4 the square, which turns out to be 768 watts. Now let's see the next question. The next question is given current 2 ampere flows through a resistor in series with a coil while 200 volt is applied across the combination of 50 Hz. He also asks if the voltage across the resistor be 100 volts while that across the coil be 150 volts. Calculate impedance, resistance, reactance of coil, power absorbed by coil, and the total power. So according to, let's see the solution. Let R1 be the resistance of unknown resistor. ZL is equal to RL plus JXL. The drop across R1 being 100 volt, current through it 2 ampere. R1 is equal to 100 by 2 is equal to 50 ohms. Net impedance Z is equal to 200 by 2 is 100 ohms. R1 plus RL plus JXL is equal to 100, and also R1 plus RL plus JXL is equal to 100. So R square plus XL square is equal to 100 square. Let's take this as equation 1. The drop across the coil is equal to 150 volts. ZL is equal to RL plus JXL, which is equal to 150 by 2, which is 75 ohms. And also RL square plus XL is equal to 75 square. Let's take this as equation 2. Subtracting those two equations, subtracting 2 from 1 will be like R1 plus RL the whole square minus R square is equal to 100 square minus 75 square. It turns out to be R1 square plus 2 R1 RL is equal to 4375, that is 4375, and RL turns out to be 81.75. From equation 2, XL square is equal to 75 square minus 18.75, so XL is equal to 76.62 ohms. Hence, ZL is impedance L is equal to 75, RL is equal to 18.75, and XL is equal to 72.62. Power absorbed by the coil is I square RL is equal to 2 square into 18.75, which is 75 watts. Total power is equal to I square R1 plus RL, which is equal to 275 watts. So that's the total power, which is 275 watts of the circuit. And now let's go to the next question. It says in the network, it's given a circuit and it's in the network, it's given I is equal to 5 and amplitude of 5, and it has a degree of 60 degree, and it's asking us to find the impedance. So solution, let's see the solution. The admittance of a given power network is Y is equal to 1 upon Z, which is equal to 560 upon 5 angle 60 upon 10 angle 30, which turns out to be 0.5 angle 30 more. Y1, the acceptance, as we see, the admittance adds up. Y is equal to y1 plus y2 plus y3. As we can, is it simple to add these values? Let's see, where y3 is equal to 1 upon z, y2 is equal to 1 upon 1 plus j2. It turns out to be 0.2 minus 0.4 j more. Y1 is equal to 1 upon 5, which is equal to 0.2 more. 0.4 angle 30 is equal to 0.2 plus 0.2 minus 0.4 j plus y3. Now we have to convert all these in a single form. So y3 is equal to point, and also we'll see y3 is equal to 0.433 plus jo plus 0.1 j minus 0.2 minus 0.2 plus 0.4J minus 0.033 plus 0.5J, 0.5 into 80, 0.5 angle 86.22 more. So impedance turn out to be 1 upon Yg, which is equal to 1 upon 0.5 angle 86.22. The answer turns out to be 0.033 plus 0.0499 J ohms. Therefore, the Z is consisting of a resistor of 0.033 ohm and inductive reactance of uh, resulting inductive reactance of 0.499 ohm in the series. Now let's go to the next question. In the next question, it's given a figure, it's given a values. It's an this is an inductor, resistor, and a Z component, where it's given R is equal to 10 ohms and XL is equal to 8 J ohms. Find G. Solution: it's the voltage is given as 50 and 0 lakh volts. I is equal to 5 as 130, so we can take it as V is equal to I upon V is equal to IZ, the total. So solution: Z equivalent is equal to V upon I upon is equal to 50 0 upon 5 angle minus 30 is equal turns out to be 10 angle 30 degrees. Z equivalent is equal to R plus JXL plus Z is equal to R plus JXL minus Z equivalent. So 10 plus J 8J minus 10 angle 30. So Z is equal to 10 plus 8J minus 8.66 minus J5, which turns out to be 1.34 plus J3. Therefore, we can write it down as 3.29 angle 66 ohm. Hence, the total the impedance of the unknown impedance is equal to 3.29 angle 66. Therefore, a series combination of resistance of 1.34 ohm and inductive reactance resulting inductive reactance of 3 ohms. Now let's see the last question assigned to me. In this, it's given in the network, given network circuit, it's asked to find XL, this inductive reactance. So let's see the solution. I1 is equal to V upon Z1 is equal to 100 degree 0 upon 20 minus 20 J is equal to 100 angle 0 upon 28.28 angle minus 45 degree, which is equal to 3.54 plus angle 45 amp. Current in branch 2 is given by I2 is equal to I minus I1, 10 degree 10 angle minus 10 minus 3.54 angle 45, which is 9.84 minus 1.74 J minus 2.503 plus J2 J 2.503. Total comes out to be 7.337 minus 4.243 J ampere. However, I2 is equal to V upon Z2, which is equal to 100 plus 0 J upon 10 plus J XL, which is 10 plus J XL is equal to 100 angle 0 upon 8.476 angle minus 30. 11, which turns out to be 11.8 angle 30, which converted into ohms, the polar form, it is 10.22 plus 5.9 ohm. So this is the given circuit. From this we can easily see this is the Z1, this is 10 and which is, and this the current flowing through is 10 in angle minus 10 degree ampere, and the voltage supply is 100 volts, which does not lag, which does not have any degree, and the total impedance is Z2. This is the resistor of 10 ohms and this inductor of XL, which we gotta find out. Now it hence this presentation comes to an end. Hope you like it. Thank you.